Okay, hi everyone. There's going to be me teaching myself elementary differential geometry. I will be using the book by Barrett O'Neill, the revised second edition. So I will start with definitions, and I will try to connect uh, what in the book with Calc 3 at the beginning. So you will be able to build upon what you know. So, I mean, prerequisite for watching these videos is you need to know Calc 3, Calc 2, these things. I mean, Calc 2, I'm not sure if you are going to use it, but yeah. And later on, maybe I will try to generalize to n dimension. So let's see. So we'll start with definitions. And Bart, what I see it's hard in learning elementary differential geometry is the notation. They have this different notation, kind of notations from calculus. So let's see. So let's try to fix that up. So the first thing is we will have x, y, z. These will be considered as a real functions, so real valid functions. On R3. And these, I mean, here they are called natural, just natural coordinates. Okay. Well, and I will do the arrow thing, which is common in algebra. I mean, x is going to be a real valid function on R. That would mean it's a function that takes input from R3 and spit out to R. Real valid. So real valid here is domain, the range is the real numbers. And what are these natural coordinates? What they do? So how they act? So for P and R3, and this P can be written as the usual way. We write it like this. Then, so the natural thing is to say x is going to spit out the first coordinate, y is going to spit out the second coordinate, sorry. Finally, z is going to spit out the third coordinate. And here, probably this is going to be, I mean, later on, to generalize, we may think about x1, xn, real valid functions on Rn such that xi for a point is going to spit out the ith coordinate. Okay. Let's see. Another definition. So we say that a real valid function f is differentiable and real valid functions on R3. So f is R3 to R, or sometimes we may use diagrams. This is most common in algebra maps. So what we will have, we say a real valid function is, so here, differentiability. Okay, if all partial derivatives exist and continuous, and f, we say it's C infinity in R3. This is a common way to write it up. If all infinite in infinite partial derivatives exists. And they are continuous. If it's just one derivative, we just not here one, but yeah. So now let's see another definition. Tangent vectors. So this is a definition. The name is tangent vectors. On R3. What are they? It's VP. Consists of 2 points. V, which is the vector part. I mean, that thing makes sense. On Calc 3, if you remember, when I started learning that, we learned, so here in Calc 3, let's just remember in Calc 3. In Calc 3, we learned that vectors are direction and magnitudes. And two vectors, the vectors, I mean, they have no initial point, they are roaming around. So this vector is exactly as this vector, as long as it's pointing in the same direction and it has the same magnitude, then they are the same vector. But now we want to be able to fix our vectors at a certain point. So here we have VP, so it consists of 2 points. One is the vector part. So 2 points of R3. Here's the thing. So the vector also, we would consider sometimes a point and sometimes it's a vector. That's natural in R3. And that's vector, so vector part and the point of application. So this is X, Y, Z. We have a point, say here. This is P. and the vector is going to be whatever. So this is the vector. Usually in Calc3 we tend to use an arrow, but here we will drop that thing. On the book they use bold. I cannot use bold, so I will just the context is going to help us and to determine what do I mean by this. And I will try my best to be consistent in my wordings. So yeah, so this is page 1. Okay. Let's see now another definition. I should maybe start check calling definitions, give a name and give a number. So this definition 1, definition 2, definition 3. I skipped some parts of the book where I feel it's very obvious. So I just jump. So at the beginning, maybe you will feel it's rushing, but then later on, I will learn with you. So it's going to be taking time for me even to get through the material. But the first thing is definitions, and definitions are very important in math. So P is a point in R3. The set TPR3 is all tangent vectors that have P as point of application. And what do we call this one? Tangent space of R3 at P. So here at and there's, I mean, clearly this is the same as R3, but so yeah, I mean, the thing is, for any point in R3 we'll have another R3 in some sense. So we have a point here. You will consider the tangent vectors, and clearly here you can go in all directions at this P. So TBR3 is the same thing as R3. It will be useful to use, sometimes to keep that in mind. For any point in R3, you will have, you can have the tangent space there, which is equivalent to R3. Let's see another definition. So here, a vector field. Okay, so this is a definition. A vector field. Vector field. V on R3 is the vector field we used to have on Calc3. So is a function that assigns to each point of R3 a tangent vector. This capital V. So capital V at P is an element of tangent vector. So VP, this one is sine, this here is so tangent vector to R3 at P. That's okay. And now we will define the natural frame. Yeah, this is important here. It should be natural frame. Frame field. So these are specific vector fields. So remember, let's just connect. So remember here, just to remind you. So vector fields in Calc 3. We used to write them as capital, maybe xy, and then it will spit out a function. It will spit out a vector again. So it takes two inputs, and it could spit out so here x plus y, x squared, y squared minus x. So here and then suppose we have a z. That's just to be consistent. So because here in the definition they have it, the vector field they define it as here in their definition, this v. If we want to write the arrow annotation, is going to be R3 to the tangent space of R3. And the point of application is, P is going to be to the is mapped to an element in the tangent space of R3. So it's going to be VP there, which is an element. So it's just so this is going to be VP, which we use also this notation, which is V subscript P, and this is element in the tangent space at P, R3. So here, the vector fields on Calc 3, it was taking 3 inputs and spit out 3 outputs. So the natural frame field on R3 are these 3 vectors, U. So remember here, we also used to write the vector field in the I, J, J, K thing. But now, this is kind of different, but it's similar in some sense. So here we have Y1 is a vector field. So here a natural frame field on R3. So here we have U1, U2, U3 vector fields. I will just write VF on R3. So that for P and R3, this P is a point. It's P1, P2, P3. So VP, U1, P is the vectors so what's the most natural way to assign a vector to this point? is 1, 0, 0, P. So, and this is U1, U2 is 0, 1, of P. It's going to be 0, 1, 0 at P. Finally, we have U3 of P as 0, 0, 1 at P. So what does this say? It says you have, this is R3. And suppose you have point P somewhere here. This is P. So if we go on this direction, this is going to be U1P. So it's like these are in some sense this is I, but this is equivalent to I. But remember here, our vectors, we can assign an initial for them. They are no longer roaming around. I mean, if we just say it's V, this is a vector roaming around like Calc 3, but this here is a vector that has initial point. This thing we didn't use in Calc 3 because most of the time we didn't use it heavily. I mean, it just was, we didn't need that. But in this differential geometry, we will need that. We will use it later on. The idea to be able to point out some initial for the vector. So this is U1P, U2P is just this J, equivalent to J, and K is going to be U3 of P. And these are called the natural frame fields. This is important to have when they start talking about the natural frame field. And remember, there's another thing that's natural. They call it natural, which was the natural coordinates. The natural coordinates are real valid functions. When you plug a point, it will spit out the corresponding coordinate. So x spit out the x coordinate, y spit out the y coordinate, etc. But now we have a vector field. Vector fields, remember, they accept, vector fields, they accept points in R3. So these UI, they are vector fields. So they are taking things from R3, and then it will be the tangent space. So here, if you here start with a point P in R3, we no longer give X as a point. So we use PQ. So if we start a point in R3, that will spit out the tangent space to R3. U1, it's going to be, it's going to be an element of the tangent space at P, and that element is going to be UIP. Okay, these are vector fields. Okay, let's move on and see. So let's solve some examples. This here, question 2 from the book. So we have V. So we start with two vector fields. On R3, V is X U1 plus Y U2, and W And I mean, here you can see something important. These UIs are bases for the vector fields. So this is interesting. So here, what we're given. So here in Calc 3, this is equivalent of giving us two vector fields. The first one is X, Y, 0. And this is here is equivalent to V. W is equivalent to G, let's call it G. And this here is 0, 2x squared, negative 1. X, Y, Z. X, Y, Z. So here, if you are familiar with linear algebra, y1, y2, y3 are bases of vector fields on R3. So any vector fields can be represented in terms of U1, U2, U3. Okay, so we were given these and they are asked us to find, so find FG real valid functions such that FV plus GW can be expressed in terms of here the type terms of U2, U. So what do we want to do? We want to eliminate U1. So we want to find FG such that we eliminate U1. And it's clear, it's not hard to see. If you multiply, so FG are real valid functions. So here this is 2x squared. This is x, and we need to eliminate that. So you multiply with negative 2x. So here if you multiply negative 2x, v plus w, you will have a 0 in u1, right? Because negative 2x squared u1, negative 2xy u2, plus 2x squared u1 minus u3. And clearly here we'll have negative 2xy u2 minus u3. And we express it on terms just u2, u3. Now we move to a very important topic in this course, which is the directional derivative. Directional derivatives says the following: if f is differentiable, differentiable real valid function, on R3, then directional derivative of f at a tangent vector at B. See here? Remember directional derivative in Calc 3. So let's just use green when we want to remember. In Calc 3, directional derivatives where, we have a function f, and the directional derivative, it was at the point, say, it's a, and this point is a1, a2, a3. Then one way to represent that was df at a, something like this. And this was the gradient of f dotted with, there was also v, which is the vector. So the gradient, there's a vector. We use also a vector in order to find the directional derivative. So we evaluate the gradient at A, dotted that with the vector V. That was the differential. And that would give us f partial xa times V1 plus f partial y at A times V2 plus f partial z at A times V3. Here's going to be the same thing. The start is the derivative. So here the directional derivative is the notation is very important. So the notation, we will use the notation, following notation. VP and square brackets of it. It's different notation. It's like VP is accepting F. It's kind different. So what does this mean? This means d over dt over d time and the time of f. And here we have p plus t v. Then we plug t equals 0. So, yeah. So remember in the limit notation, this tells t approaching 0. And we will have f of p plus tv minus f of p over t. That's the directional derivative. And yeah, it can be proven that, I will not prove it, but it can be proven that on this here, so lemma, v, let's just be consistent with the notation. Small v when it's a vector, so I will use here, I will use small v for a vector, capital V for a vector field, because we will see later on, we will use that. Okay. This here equals to the sum of vi, the coordinate of vi, times the derivative at the ith component p. So maybe I skipped something about the um, yeah, I mean it was unexpected here. They used uh, partial f partial xi, but this is, I mean, this is completely understandable. What does it mean? So this here f accepting three inputs. So um, partial f partial xi is is the derivative is the derivative with respect to the ith component, is the derivative to the ith component. I mean, yeah. So here, this what is this going to give us? V1 partial f partial x1, which is just x. Then we plug p there. Then we will have V2 partial f partial y. You plug a b, p. Then finally, we have V3 partial f partial z. We plug a p. Okay, and we have interesting properties here. VP WP two tangent vectors at P, FG real valid functions, then we have the following. We have, if we, so direction derivative is derivative, but it accepts three things. So let's just write that down. It's just, I mean, directional derivative accepts three things, or takes, let's just say it's takes, because accepts. So it takes three things: function, vector, point. So this point we cannot play with, but this vector we can consider two vectors, sum of two vectors. And this function we can consider sum of two functions. Then we can ask, is the direction derivatives of the sum of two functions the direction derivative of the individuals? We can ask also, two tangent vectors, is the sum of the two tangent is the direction derivative of a function of the sum of two vectors is the sum of the directional derivatives, etc. And that's what this theorem says. So it's the linearity. So here linearity, so this is linearity of tangent vectors. And we have another one which is going to be linearity with the other. So here we will have A, VP, we apply F, plus PW, we apply G. We'll have another linearity. So we have VP. By the way, A and B are just now, for now, they are just real constants. So they are constants. They are not nothing else. So G. Now the third one, remember, product rule. This is a version of the product rule. Anything that has a product, anything that's derivative is going to be having the product rule. Anything we say it's derivative, it will have the product rule in it. So this is interesting. So here, VP of FG is VP of F. We multiply that with GP at point P. Then we will have the other things. So FP VP at G. Okay. Another definition. Let V be a vector field. Remember, vector field, what does it do? It accepts something in R3 and spit out something in the tangent space. So it will spit out something that lives on the tangent space at that point. So VP is an element of the tangent space. Then what we can do now, we have the directional derivatives. We can do directional derivative at that thing. So see, because this here is an element of the tangent. Say it's WP. Then you can apply directional. This is directional derivatives. And we will have kind of similar things now. Now we will have f, g, real valid functions. H also. V, W vector fields. All of these are normal. Then, for any point, I will drop it, but for any point, f, v, g, w. So what is this? This is directional derivative. This here is the directional derivatives. And this here is the vector part. And this here is the function we derive, real world function. This would give us the obvious thing. Plus See here we dropped, so here we dropped P. So here, the point of application, the point of application is dropped. So that would hold for anything. P is dropped. This is the first one. The second, now we have a vector field. We can apply a linear combination of two functions on it. And that would be applying V to the individuals. Lastly, we will have something like the product rule. Vf dot G plus F dot F of G, V of G. Now let's solve some problems and end with it. So we have V equals U cube U2 minus X U1 F equals Y X squared and G is Z squared. We need to find, so find F V G minus G F. Okay, this is interesting. This is interesting. So I will apply a point to make things easier and understand what's going on. So let's see. So yeah, so you just plug the function. So here we have y x squared v g is z squared minus g is z squared v of y x squared. Okay, what next? Let's see. Y x squared. Now, how to apply z squared onto here? This is the directional derivatives. This is the directional derivative of z squared in the direction of this vector. So this is the directional derivative. So remember, what we will do here is we will derive this. So here, partial z squared partial x plus partial z squared partial y plus partial z squared partial z as the derivative. But then we will apply a point, and when we don't have the point, we'll just keep it like this. And yeah, I should be more careful. I mean, I will use like calc 3. This is a vector. And I want to dot that with the vector field with this one at the point. So I will dot that with negative x, y cube 0. So this here is 0, 0, and this one is 2z. We dot that with negative xy cube 0. So this is 0, just 0. Let's see the other term. I'm still learning, so it takes me a while to figure it out. Negative z squared. Now, what we will do here, we can use the, I will not use the product rule for sure for this one. So v again, so I will just write it like this here. So negative x y cube 0. And we dot that with the yx squared, what we derive it. So here it's going to be 2xy. Then you derive it with respect to y, so it's x squared 0. And you just combine these up. So it's negative 2x squared y plus y cubed x squared. Multiply that with negative z squared. And that's what we do. That would be our thing. Okay, is there a faster way to do it? That's a good question. I don't think so. Yeah. So maybe here, if I want to use the notation of the book, let's see. This should be partial z squared partial xi times vi. So partial x squared with derivative with respect to x, this is 0. This is going to be 0 because x1 is just the derivative with respect to x. v1 is the coordinate of u1 there, up there. So it's just going to be like that. Plus, now the derivative with respect to y is 0. And the second coordinate is y cubed. Plus, the derivative with respect to a third is 2z. We multiply that with 0. So this is going to be 0. Yeah. Also, yeah. Also in the book, they swipe these. This is in the beginning. So let's do the other one using the book way. So yx squared. This here is vi partial what's inside partial xi. And this here is the inside here. Okay. So what's going to be? So we have v1 again is negative x. We multiply that with derivative with respect to x, which is 2x y. Then it's going to be plus y cubed. We derive this with respect to y. It's just like this. Lastly, it's 0 times 0. And we will end up with that. What else we can do? There is another interesting one we can think about, which is the following: VF. This is interesting. So VVF. So the first thing we apply, let's see if we can now master it up. So this is going to be I will expand the inside first. Is V1. So V1 is the vector, so it's negative x. So let's just ignore the summation and do it directly. So V1 is like this, then partial this with respect to x, then we have y cubed. We differentiated with respect to the we differentiate it with respect to the y, so it's x squared. So now we have v negative 2x squared y cubed x squared. Okay, let's use the product rule and use linearity. Why not? And remember, we can write that as v 2x squared y plus v y cubed x squared. But then we can use linearity. We can use the product rule. Remember, there's a product rule version, which is this. So let's use it. Let's use it. So let's just write it down, then we use it. Okay. Let's use the rule. So the rule says VFG is going to be FVG plus GVF. So we have V negative 2x squared y. This can, negative 2, remember, can be split out. So we will have times yvx squared plus x squared vy. Now the interesting thing, this one has just derivative with respect to x, and everything else is 0. So this is just going to be multiplied with the so here, remember, this here is the summation of vi times the derivative of this here, derivative of x squared with respect to xi. But here we just can derive it with respect to x. So the only thing that will worth looking at is the derivative, which is this thing. So it's negative x times the derivative with respect to x, which is 2x, plus x squared. And here again, the only thing is you count is what next to u2. So there's going to be the derivative of this, which is 1 times y cubed. So it's going to be like that. The other one is the same thing. I will end it up here, and we will do more later on. That's for today. Thanks for watching. That's it.